A researcher wishes to test the effectiveness of a flu vaccine, so he gets 150 vaccinated people, 180 placebo vaccinated people, and 100 people not vaccinated, and tracks them, and later finds out that uh, for the vaccinated group, 8 people got the flu, placebo had 19, and control had 21. And he wants to figure out whether this is a good enough evidence to say that vaccination does work. So the way you phrase this in a contingency table with the chi-square test of independence is like this. You take the null hypothesis as whether or not one catches flu is independent of vaccination. Of course, if the vaccine is ineffective, then there would be no difference between the placebo or control or vaccinated. But the alternative hypothesis would be whether or not one catches flu is not independent of vaccination. Okay, or this is phrased a little strangely, but anyways, whenever you have a chi-squared test of independence, the alternative hypothesis is always not independent. So keep that in mind. All right. Okay, so let's proceed. To do the chi-squared, this is the test statistic. It measures how different is the actual observed value and the expected value. So you take the difference squared and you normalize it by dividing by EIJ. So this is kind of a score that measures how far your observed is different from expected. And if you get a high score, that allows you to reject the null hypothesis and then adopt the alternative hypothesis. Then on top of it, you have to know the degrees of freedom to actually calculate the p-value for this test statistic. And for the contingency table, it's always just row minus 1 times column minus 1. There's a reason why it's this. It's just a number of free variables if your total is a fixed number. But then since this is always the formula to use for the contingency table, you might as well just memorize this. In our case, the data part is actually 2 rows and 3 columns. So it's 2 by 3, so 2 minus 1 times 3 minus 1 gives you 2. And then in order to use this formula, then you need to calculate the expected value by this formula right here. And because you need the total of the rows and the columns, let's first populate those numbers. So if you add them, you get 48. You add it vertically, that's the column sum, that gives you 150. And 430 would be the sum of everything. And the way you calculate for E11, for example, would be multiply 48 times 150 and divide it by 430, the grand sum, which gives you 16.744. So that's going to be the expected value. But as you can see already, that though you're expecting about 16.7 people to catch the flu, the vaccinated group only has 8 people catching it. So there's something going on here, right? Like it seems to reduce the percentage of getting the flu. So this looks already hopeful, but in order to really know the significance of this result, you have to add them up, and well, you have to calculate this, add them up, and then use the chi-square to calculate the p-value. All right, so I'm going to write down 16.7 as a parenthesis, so to keep in mind what the expected value should be. And then you do the same thing for the next one and the next one, and you get all these numbers. So for example, 20.1 would be 48 times 180 divided by 430. That's 20.1. So you populate it, and then now you can calculate the chi-squared by subtracting these two numbers, and squaring them, and then dividing by the expected number, the thing inside the parenthesis. And finally, you get this value of 14.97. So we get this 14.97 with degrees of freedom 2. What does that mean? Well, that means we can calculate it by going to second vars, and then you can go to chi-squared CDF, and don't touch the lower, just put the 14.97 as the upper and put the degrees of freedom as 2, paste it, and that gives you 0.999. So it's a very high value, right? But really what's needed is 1 minus this. That's because the chi-square graph looks like this, and the 14.97 is a very high value. And what we just calculated with the calculator was the area from 0. Actually, it starts at 0 here. From 0 until here. And that's about 0.999, which means the probability of getting some value of chi-squared as between 0 to 14.97 is 0.999. But because we want to know how significant this 14.97 is, we phrase the question as like, what's the probability of getting 14.97 or something higher than that? That's called a p-value, right? So for that p-value, you actually have to subtract from 1. So let's do this. Let's do 1 minus second vars. Go to the chi-squared CDF, put everything there, enter, and you get 5.6144 e negative 4. That's your p-value. Okay, so let's see. Your p-value is, oh, what happened? 5.6144. 5.6144, that's your p-value. And then e negative 4. Now, a few people get confused if they see this e negative 4. What this means is, it's like 5.6144 times 10 to the negative 4th power. It's a scientific notation. And in order to change this into a regular notation, you have to keep in mind that negative power means fraction. So you get 5.6144 divided by 10 to the 4th power. Well, 10 to the first power is 10, 10 to the second power is 100, 10 to the third power is 1,000, and 10 to the fourth power is 10,000. So that's what you get, and that value would be 0.000. So it's one less zero than what you have. So if you divide by 10, there won't be any zeros, but if you divide by 100, it'll be 1 0. So if you divide by 10,000, you'll have 3 zeros, and then you have 56144. Okay, so that's the value of p, and that's definitely less than the significance value, right? So the significance value is 0.05, and therefore we can say that we reject H0 and conclude that the vaccination status and catching flu is not independent, which is to say that the vaccination has some influence. And actually, looking at this table, it seems to indicate that the vaccination is helpful.